Hello, Professor. Today I want to introduce the lecture file summary. I'm today's presenter, Jiajun Jiang. Here's the agenda we are going to follow. We are going to start with the performance because this is really how the pipeline doing, and then is how the pipeline can do, and which problem we might encounter, and how to deal with these problem, and then is the ILP and the VLIW. So let's start with the performance. The performance, there are three main ways to measure the computer's performance. And the first one is execution time and latency, and then is throughput. The execution time is from the work start to finish. Or latency is amount of time that it takes one instruction to execute. The throughput is how much work can be finished in 1 unit of time. And in non-pipeline processors, the throughput is 1 over latency. And pipeline processors' throughput are bigger than 1 over latency. Of course, when we use the pipeline, we have better performance. Otherwise, we won't use that. What exactly is the pipeline? The pipeline is a technique that makes multiple instructions run overlap execution. Means we want the CPU can do the fetch, decode, execute all the time. And overlap execution can be increased hardware efficiency to increase the throughput. The pipeline is made the job separate into different steps and do it separately. There are 5 stages in MIPS data path. The first one is fetch, then second is decode, third is execute, the fourth is memory, and 5 is write back. And here's the data path in MIPS. We can see there's a 4 latch separate the data path into 5 stages, and just the 5 stage on the previous slide. And we just see the throughput is 1 over the latency. So how do we calculate the pipeline latency? The pipeline latency is product of number of pipeline stage times clock cycle time and minus latch delay. And how do we calculate the circle time in pipeline is equal to circle time on pipeline over number of pipeline stage and plus pipeline latency. And the pipeline's characteristic. And the first characteristic is pipeline won't change the latency, but can increase the throughput. And how the pipeline can increase the throughput? Because it increases the usage rate. And pipeline limited by the longest pipeline stage. Because every stage have different latency, but we have to choose the longest one. And here's the example is easy to make us to know how the pipeline doing. And we can see there's a 4 instruction. First one is load word, store word, R-type, and branch. From the table, we can see one single load word needs 800 PS to execute. And if we have 3 load words instruction to run, if we use single circle machine, we have to use 3 times 800, so it will equal to 2400. But when we use pipeline machine, it will only use 1400. So when the first one load word are already fetched the instruction, go into the decode, the next instruction load word can use the fetch. So that's the reason why the pipeline can increase the usage rate. Obviously, the pipeline isn't the perfect, so it will encounter 3 types of hazards. The first one is structural hazard, and it means the hardware resource is not enough. And the second is data hazard. When an instruction depends on the result of the previous instruction, it will become the data hazard. And the last one is control hazard. When branch and other instructions are not ready to decide, it might change the PC, and the instructions from the back are already in the pipeline, it will cause a control hazard. And it also called branch hazards. And we can see the structural hazard. We can see the right picture of the slide. The instruction 1 and instruction 4 are using the same memory in the same clock cycle time. The structural hazard is the most easiest one to deal with because if we add more hardware resource, it will be just fine. Because like if we add 2 memory or 3 memory or more memory, and the CPU can use the different memory to fulfill all the instruction. So this is kind of easy. And then is the data hazards. We can see the right picture. There's a lot of instruction want to use the same register, but we have to wait the instruction 1 right back to the register, so other instruction on the back can get a correct value in the register. So the data hazard will happen when one instruction are reading the register, but it gets the old value, so it will cause the data hazard. And then is the data dependency. The data dependency is the main reason why we'll encounter the data hazard. So there's a 4 type, and is read after read, read after write, write after read, write after write. But the read after read won't cause anything, so I will focus on the other 3. And is first one is RAW. It's the most common type. It arises when the next instruction tries to read the source before the previous instruction write to it. So the next instruction get the old value incorrectly. And then is WAR. The WAR arises when the next instruction write to a destination before the previous instruction read it. In this case, the previous instruction get a new value incorrectly. And the third one is WAW. The WAW is a situation when the next instruction tries to write to a destination before a previous instruction write to it, and it is result in change the down in the wrong order. And the WAR and WAW hazard won't do any delays, only the RAW will cause the delay. And here's the method for the hardware to deal with the data hazard. It's called forwarding. In the forwarding, we have add some special hardware to get the data previously, so we can make sure when the reading data, it can get the correct one. The picture we can see the forwarding can make the result of the execution stage directly to the instruction in the previous stage of the pipeline. So when the result is come out, we just forwarding the result before the register can read, forwarding the data to the stage we need. And then is the control hazard. We can see the picture. The BEQ doesn't know the results after stage 3, but the next instruction are already running. So if the BEQ wants to jump to the instruction 4, but we already waste the time and the resource to run the instruction 2 and instruction 3. So it will cause a control hazard. And we will talk about this on the next lecture. And then is the instruction level parallelism. The superscalar processor can run the multiple instructions on the same time because it has the multiple execution unit. Here's another processor called VLIW processor. It also have multiple execution units. The compiler to decide which instructions should be executed in parallel. So the compiler have to know how many execution units we have. And the multi-processor case, it has multiple core. And then is the instruction scheduling. How do we speed up the execution time by using the pipelining? We can see if we want to make the instruction run in parallel, we can make the instruction, we can separate to A and B. A means those 3 instructions have the data dependency, and the B has another set of data dependency. So if we run the program using 2 execute units, we can reduce the clock cycle from 5 to 3. So the advantage of when we using the ILP, we can obviously speed up the executing instruction in parallel, but we still have some disadvantage in ILP. For example, we still have to face the dependency in the data and the name. And even we have like 100 execution units, we still will encounter the dependency. If we have like 1,000 execution units, but we still cannot reduce the clock cycle to 1 because we can see there's a 3A, so there are dependencies. So even we have a lot of execution units, we still cannot reduce the clock cycle under the 3. And is the in order versus out order execution. The in order means when we execute instructions, they will follow the sequence just like they are in the program. And the out of order means when we execute instruction in any order, that won't change the result of the program. And the out of order execution is much difficult than the in order execution because it still have to follow instruction dependency, and when the computer try to find out the best instruction order will cost a lot of time. The time will grow exponential with the instructions. And the register renaming, when the data hazard like the WAR and WAW, why will happen the data hazard? Because we don't have enough hardware resource to fulfill all the instructions, so makes the computer have to reuse the same register. So we can see the picture, the left one, it used the twice F-link when it load the register, but the right part, when it used the F0 second times, it will change to the F6, so it is called the register remaining, and also the F4 changed to F8. And the register renaming also can increase the performance, because if we use the register renaming, we can get rid of the read after write and read after read. And then is the VLIW processor. The VLIW means the very long instruction words. It is a processor architecture for increasing performance by processing instruction in parallel. In the VLIW architecture, different independent operands are defined with each instruction, which are executed by the hardware in parallel in several execution units. The number of execution units determine the number of operands of the VLIW instruction, which operation of an instruction are proceed in parallel in determined by the compiler. In the VLIW architecture, an instruction logic loads the VLIW instruction from memory in one circle and pass it to the execution unit. So the VLIW makes the hardware very simple, but makes the compiler become very, very complex. So the pros in VLIW processor is the hardware is very simple and potentially more scalable. But it also have cons. The first one is compiler too complex and longer compilation time. Unhazard all feature issues stall until hazard is resolved. And the last one is need a lot of program memory bandwidth. So this is all I have today. Thank you, Professor.